Yeah, I think without any further ado, I'm gonna pass it over to Sora and Enrico, right? Who's gonna tell us a bit more about indistinguishability, obfuscation, and how Machina is developing Diamond IO in this space. So yeah, over to you.
Yes, thank you for the introduction. So I'll start our presentation. Can you see this right?
Yes.
Okay, thank you. Okay, yes, we'll start our presentation. So hi everyone. Thank you for coming here today. So our team, Machina IO, is within PSC Research, is working on practical IO. And I'm Sora, as a leader of this Machina IO, and the other member is Enrico and Pierre. So today, we'd like to talk about how to scale privacy with indistinguishability obfuscation. So this is today's outline of today's talk. And here, we'd like to answer these three questions. So first, what are IO and its application for Ethereum? In short, IO is a cryptographically secure program compiler. And this, as its applications, this enables untraceable mixing for today's crypto users, and also a privacy-preserving matching for new types of users. Then why should we use IO rather than MPC, FEG, or TE? So this is because, so we believe this is because only IO can preserve the guaranteed privacy level, or even as the application's handling value and scale grow. Then, how can we make practical IO? We still don't know the complete answer, but Diamond IO, an IO construction we proposed and implemented, solves the biggest bottleneck of previous construction by replacing it with simple matrix operations. So today we'll explain the detail of these answers. And first, we explain about the definition and feature of IO and its applications for Ethereum. So have you ever heard IO, indistinguishable obfuscation, before this talk? So you can see IO as a program compiler. So by providing a program represented by as a circuit for this IO program compiler, you can get the obfuscated circuit. And in the same way as the standard program compilers, this preserves the same functionalities, which means the obfuscated circuit returns the same output as for any input as the original circuit. And in practice, you can use IO by making your circuit hard coding some of your secrets or secret algorithms and broadcasting this obfuscated circuit through the internet or any public channels. And anyone who downloads your obfuscated circuit can evaluate your circuit on any inputs. And they don't need to interact with you or obfuscator, so that you don't need to work anymore once you publish the obfuscated circuit. And in a real application, especially for smart contracts, we cannot assume one trusted party who knows everything inside the obfuscated circuit. And in these cases, we can usually assume that the functionality of the circuit is public, but we have to hard code some private keys that should be unknown to everyone. So in such a case, we can obfuscate the circuit or in your distributed setup, in similar to the trusted setup ceremony of the ZKP or KZG commitment. So that as long as one party is honest, and that this person removes the randomness after the setup, no one will be able to recover the hard-coded private key inside the obfuscated circuit. And the biggest difference of this IO compiler from the standard program compiler is its security guarantee. And there are two formal definitions of the security, IO security. So the first one is indistinguishable obfuscation. And its good point is that it can be constructed without any heuristic assumption if we don't consider the concrete efficiency carefully. However, this definition is not straightforward because this can protect the privacy inside the obfuscated circuit only when you can also describe the same functionality but without hard coding any secrets. So this is weaker than the one more security definition called ideal obfuscation. And this ideal obfuscation provides the security or what you expect, which means the obfuscated circuit reveals no more information beyond its input-output pairs. However, its construction definitely requires theoretically or heuristic assumption, specifically pseudo-random oracle. However, this random oracle can be just implemented by a hash function in practice. And we already employ this kind of assumption in ZK scheme or FEG and so on in practical systems. So we think we should finally achieve this ideal obfuscation. And fortunately, if we can make indistinguishable obfuscation, we can easily extend this to ideal obfuscation just by adding our hash function and the public key encryption. Then, how is today's indistinguishable obfuscation practical? So in one of the latest research, but in 20 research in 2015, it reports that the simulation result of the practical simulation result of the obfuscation time for circuit with input size and the multiplicative depth 3 is simulated to be more than 2 power 27 years. Yeah, so this is I think this is maybe longer than at least the Earth or maybe universe. But in contrast, with our IO implementation, Diamond IO achieves the obfuscation for almost the same scale of the size, around the 6 hours. So maybe you still feel 6 hours for just for input bit is still impractical. Yeah, and this is correct, but this result is already a significant improvement of the concrete efficiency of IO. So these are like a definition and the properties of the IO itself. Then, how can we combine IO with Ethereum, and what kind of application can we make? So fortunately, IO and Ethereum are complementary because while IO can obfuscate stateless programs, Ethereum can provide trustless persistent state management layer, so that we can manage the encrypted states output by the obfuscated circuit. So by simulating the reading and writing of the encrypted state, we can build the private smart contract like this one. So the point here is that in similar to our smart contracts, this can receive the input from users and make some outputs while updating the state data. This can encrypt this input and the encrypted state data. So in the best case, if we need a private smart contract can protect the privacy against any humans, while it can allow anyone to use and update the state data or encrypted state data only by following the predefined logic of this private smart contract. Sorry. So, so then, how can we make this private smart contract using IO? So we can consider using ideal obfuscation to obfuscate the circuit with this kind of design. So you may feel this is too complex, but the point is that first it takes as input 3 inputs: consensus proof, encryption of input, and encryption of the previous state. And it first verifies the proof to check that these encryptions are actually recorded, and the block containing these data are finalized by the Ethereum layer 1 validators. And if this is true, this decrypts these encryptions by the private key. And here, we can directly hard code private key inside the obfuscated circuit. And next, we perform some application-specific circuit evaluation using these decryption results. And it can output the plain text of this circuit output. And after that, this circuit encrypts the next state and as a public key, and outputs state encryption. And by using this output encryption of the state as the previous state in the next execution of this private smart contract, we can update the encrypted states while keeping it hidden from people. So, sorry, I tried. Okay. Or maybe you can see some red line. Okay. So, using this private smart contract, we can consider two types of the application. First one is for today's Ethereum users, while the second one is the second type of the application unlocks entirely new segment of users for Ethereum ecosystems. So first one, untraceable mixings solves the problem that anyone can detect if this address has used mixing service or not. And this is possible because in the current today's mixing systems like Troned Cash, every token should gather, every mixed token should gather in the same common address, such as Troned Cash smart contract address, so that people can check if this address withdrawal address has interacted with such common address or not. So we solve this problem by removing such centralized such common address and making any mixing transaction indistinguishable from EUA transfers. So this is possible using private smart contract in 3 steps. So here we consider Alice and Bob want to do mixing with each other. And Alice has a private key, public key, EUA denoted by A0, and Bob has a private key, public key, EUA denoted by B0. So Alice first sent her public key to private smart contract. And this process is encrypted and anonymized because actual message can be sent through some permissionless layer similar to the current mixing service. And then this private smart contract will issue new private key and its corresponding EUA denoted by A1, and store this private key in its encrypted state and outputs the encryption of this EUA A1. So Alice now gets the EUA A1. And Bob does the same process so that our private key issued for both B1 is stored in the encrypted storage, and Bob can get the EUA address B1. And in the second step, Alice and Bob makes the EUA token transfer from her EUA address to the provided EUA address, like this one. And then each of them submits proof of token transfer to the private smart contract. And this specifically proves that a token transfer transaction is finalized on the Ethereum layer. And this such block is actually verified by more than threshold number of the Ethereum validators. And In the final step, once both parties, all participants of mixing are completed or transferring, sending their is to the deposit addresses, private smart contract reveals the private key of the other party issued for the other party. For example, issues the private key B1 for Alice after encrypting this under the Alice public key. So Alice can now get the private key B1, and Bob can also get the private key A1 by the same process. So this means, or this implies, Alice can withdraw the is sent from the Bob's original address to the EO address B1, and similarly, Bob can withdraw is sent from Alice to this EOA address A1. So we can summarize its token transfer history like this one. And this is also equivalent to the information you can see only from the public blockchain information. So surprisingly, there is no connection between the old and the new address of the same person. So in other words, they can exchange the token history. And also, if more transactions with similar patterns occur around the same time, it becomes harder to identify Alice's new address. So for example, while we can know that Alice Ether is sent to this address, Bob's new address, we don't know whether this one or this one or this one is Alice's new address, because everything is just EUA transfers. And this also means we can also count the EUA transfers, not the mixing transactions, as a set of the as a source of the anonymity, or because this also includes the candidate of the potential user's address. So in this way, this can significantly increase the anonymity of the mixing, and it makes it super difficult to detect if they have used the mixing service or not. Okay, so next application is the private matching. So we define our private matching as a protocol which keeps each participant's private data hidden while outputting some optimal matching result, which is computed from the provided private data. So we can consider a lot of types of the application. It is not only individual matchings between individuals just for dating, but also matchings between countries or for some nuclear fuel swap and so on. And the important point of this application is that our matching results are useful not only for existing today's cryptocurrency users, but also for other users. So we believe this can unlock an entirely new segment of the users for the Ethereum ecosystem. And also, we can find the positive feedback loop in private matching. So this is because more and more private data are delegated by users, then they are accumulated. More and more valuable data, we can say more and more valuable data are accumulated on this private smart contract, so that this more data will improve the quality of the matching output. So better matching output will collect more users' data, because this is just useful. And then this again accumulates more value of the private data. Then our question here is that what is the maximum theoretical maximum limitation of the value that private smart contract can accumulate? And this answer is also related to the question that why should we use IO rather than MPC, FEG, or TEE? So our answer is that only IO is are scalable. Only IO can provide scalable privacy when the value are delegated to the such private smart contract or private privacy preserving technology or increase. So we consider the relation between the provided privacy according to the delegated value, accumulated value. And we say, or we define privacy as some kind of inverse of the probability that data breach occurs. So for MPC or large-scale feature or TEE, which relies on or some trusted committees, or then or when more and more values are accumulated, more and more valuable private data are accumulated, or we think the data breach probability will increase, which means this reduces the guaranteed privacy level. This is because if the committee has twice amount of the valuable data, they get their incentive to behave maliciously collude and sells some like a private data by silently decrypting them will increase. So when we consider how the accumulated value on this platform based on a private smart contract, privacy competition platform based on private smart contract increase according to time transition, when more and more data, private data, more and more valuable data are accumulated, this decreases our guaranteed privacy level in the case of existing technologies. So this decreases the user's trust in the platform, this private smart contract. So this implies the growth rate of the data volume or value will decrease, even if the accumulated value itself will somehow increase. So we can conclude that when the growth rate becomes finally zero, the accumulated value of this private data is bounded, so that we think as long as we rely on some trust assumption on committees or people, that our accumulated value or private data based on this technology will be bounded. In contrast, we can say IO does not have such decrease of the privacy because IO no longer relies on or continuously relies on such trusted parties. So this does not have any factors which decrease the privacy due to the human reason, which is rated to the accumulated value. So this implies we can remove these negative factors in the case of when we use IO. So we can overcome this bounding limitation. So the accumulated value of private data when we use IO will increase battery without limit. Yeah, but you may think this is too ideal, like our estimation. And in fact, we also think there are still remaining limitations even if we use IO. And first point is the trust assumption in the distributed trust setup. However, for this point, we think this trust assumption will hold with super high probability because at least one party needs to be honest only during the first setup phase. In other words, as long as one party discards the randomness after the setup, no one will be able to break the security of IO as long as IO scheme itself and its implementation is secure. And the second point is the trust assumption in the Ethereum layer 1 validators, because the private smart contract based on IO still relies on state management or state consistency check based on the trust in the Ethereum validators. However, if we suppose that our IO evaluation cannot be executed within the MPC in practice because it's too heavy, or we can say colluding parties who tries to make the private one of the colluding validators who try to make the private fork of Ethereum and silently decrypt or some private data by hacking the IO system. We will need to output the proof, output the consensus proof, which includes a list of signing validators as a plain text. So one of these colluding party reviews this list of the consensus proof, we can publicly detect such attack. So even if we still have this trust assumption in the Ethereum layer validators, we think this assumption becomes weaker compared to using the relying on the MPC or FEG and so on. So these are like applications of IO, and the reason that we think we finally need IO. Then, how can we make practical IO construction? So since 2013, many approaches of IO construction have been proposed, and most of the recent constructions built cryptographic primitive called functional encryption instead of directly going to IO. Functional encryption, in short, FE, is a stronger version of the public key encryption, such that a secret key is associated with some circuit, and the decryption process outputs not the plain text in the ciphertext itself, but the circuit evaluation result on the plain text in ciphertext. So if we say this plain text is X and the circuit is C, this output CX rather than X. And this transformation from FE to IO is very costly because this requires recursive FE encryption for every input bit. In more detail, we have to express the FE encryption algorithms of this FE as a circuit associated with the secret key. So this is very inefficient in practical, in the similar reason as the complexity of the recursive ZK, which describes the ZK verification logic inside the circuit for proving process, or FEG decryption, which describes the FEG decryption process inside the circuit for FEG evaluation process. So we solve this problem by directly constructing IO without relying on traditional FE to IO transformation. And we replace this recursive encryption process with simple matrix operations. And we can achieve that by using the FE scheme introduced in the paper denoted by AKY24 in a non-black box way. And the security is proven under the LWE, evasive LWE, and our new lattice assumption called all product LWE in the slow random oracle model. And the latter of these two assumptions are still non-standard assumption. But for the evasive LWE, we confirm that any known attack on this evasive LWE cannot be applied to our construction. And also for our assumption all product LWE, we researched what's the missing piece to reduce this assumption to the standard LWE assumption. And our key technique is illustrated here. So this vector and these matrices at each left and right side are provided by the obfuscator as a part of the obfuscated circuit. And the evaluator just need to multiply either this one or this one to the given vector one by one for every input bit. So for example, if the evaluator's first input bit is 0, evaluator just multiply this matrix by this vector so that it can get this vector. And the evaluator just need to repeat this multiplication until the last input bit. And by doing so, we can get essentially the same output as the cost-free F-free recursive encryption process. And we not only propose the theoretical construction, but also implement this idea. And then we confirmed the end-to-end process of our indistinguishable execution in more detail, in more specifically in I/O for slow-random functionality is completed in the end-to-end workflow. And one note is that after we implement this and measure the benchmark, we found that the complete implementation of the slow-random function adapted only to the implementation might have some security issues. So maybe we need to update that construction to make it secure, and the benchmark will change. But even in this case, the benchmark even in this case, the implementation already includes our key trick, which is which replaces the recursive FA encryption with the matrix multiplications. And these are benchmarks of the end-to-end flow. And you can see that for input size 4, this takes around 6 hours. And the obfuscated data size for the same input size is around 65 gigabytes. So yeah, this is definitely larger than any cryptographic schemes like ZKP or FEG. And we understand this cannot be scaled into the more larger input, practically large input size in the same approach. However, again, this already significantly improves the complete efficiency from the previous simulated result of the I/O construction. So next, so from this step, we next target increasing the input size as our concrete technical milestone. And this is because if we can increase the input size so that we can input the FEG ciphertext and the ZKP proof for the obfuscated circuit, then we can obfuscate the border class of functions by using by only obfuscating the circuit for FEG decryption and the ZKP verification. In other words, the process to scale the complexity of I/O is not like a linear one, because once we can achieve this like a technical concrete or specific or complexities for FEG decryption and ZKP verification, we can more easily extend its scale just by increasing the complexity of the FEG and the ZKP, both of which are more efficient than I/O. And this is our concrete roadmap to achieve this. So we are now researching a more secure and practical PLF construction compatible with I/O, with our Diamond I/O. And also we started working on the GPU acceleration of the lattice operations. And from theoretical perspective, we are researching the more minimum security assumptions sufficient for practical I/O construction. And from efficiency perspective, we are researching a new way to scale the input size more easily. And once we can achieve a sufficiently large input size, we will be able to support ZKP verification and FEG decryption within I/O. And this unlocks a lot of practical application. So ideally, if we can achieve this within a few months, we want to present some demo applications such as demo application of I/O, such as untraceable mixing at DevConnect. So okay, let's conclude today's talk. So we had 3 questions. So first, what are IO and its applications for Ethereum? IO is a cryptographically secure program compiler which provides securities based on cryptographic assumptions. And this for Ethereum, by combining IO with Ethereum, this enables untraceable mixing for today's crypto users and the private matching for new segment of users. Then why should we use IO rather than MPC, FEG, and TEE? This is because only IO can preserve the guaranteed privacy level. In other words, this can scale the privacy even as the application's value and scale grow. And finally, how can we make practical IO? And we are still we're still researching how to make the practical IO. But one approach we achieved is replacing the biggest, replacing the costly or recursive encryption process, which is a common bottleneck of the previous construction with simple matrix operations. So we achieve the implementation of the IO with a reasonable time. So so this is a link to our website and the blog post about our IO implementation. And yeah, we understand we are still at our starting point towards for the goal of our practical IO. Yeah, but we are looking forward to so we want to research more ideas, more practical and theoretical, and more ideas both from the theoretical and the engineering perspectives. And we want to keep writing papers and building our products codes. Yeah, thank you for listening.
Thank you very much, Sora. Thank you so much. We have a few questions, so
Yes,
let me present them.
yes.
One question we have here is the transfer amount, 0.1 ETH or 1 ETH, relevant to define the anonymity sets?
Yes. So I think if we use our mix, if we use this like a mixing idea only on like a layover or like it's like an independent application, I think anonymity set is very important and rated uh, because I think maybe it's okay to like adapt the various amount, but to maximize the anonymity, yeah, I think we should use the same amount. But one idea to change this amount or to support the arbitrary amount while keeping the privacy is that if we assume that like this, we have some layer 2 systems which recognize the address provided by this IO or private smart contract as the deposit address to this layer 2 system, and then like we can say the process to send is to the EU address provided by our private smart contract is corresponds to the depositing process, and the process to obtain the secret key of this address from private smart contract corresponds to the withdrawing process. And if users can make transaction within the private smart contract as if like they are doing the exchanging the ETH within some layer 2, then it's possible to allow user to like deposit or so it's possible to support the case such that user only deposit 0.1 ETH but finally withdraw 1 ETH as long as user collects 0.9 ETH within this like layer 2. So in this case, like we can more randomize. So we cannot we can more randomize the relation between the deposit amount and the withdrawal amount.
Got it. Okay, thank you. Sorry, you're
Yes.
still sharing your screen. I don't think
Okay.
you need to.
Okay. Thank you.
Um, we have another question here. Out of all the L1s and L2s, which do you think are best suited to integrate with IO? And what needs to improve with Ethereum? So it's sort of two questions, but can take it one at a time.
So first question is which is more comfortable with IO layer 1 or layer 2, right?
Yeah,
Yeah.
maybe there are some specific L1s or specific L2s that are best suited to integrate with IO.
Yeah. So first, I think our our the best layer 1 protocol suitable to IO private smart contract is Ethereum. This is simply because Ethereum now provides as far as I know, this provides best security, best layer 1 security, and this also supports our smart contracts. And also, for the discussion between layer 1 and layer 2, I think this depends on the application. So, for example, for the application like mixing, building like a layer 2 or integrating this to layer 2 to like to like anonymize the deposit and withdrawal address might more make sense. But for the other application, like for example, for application like trustless Bitcoin bridge or integrating this directly on layer 2 might more make sense because their interest is to like issue the wrapped Bitcoin on like Ethereum, and it's better to issue the wrapped Bitcoin directly on layer 1 and moving this wrapped Bitcoin itself to any layer 2 later.
Are there any Ethereum protocol changes needed for some use cases, or do we need to improve Ethereum in some way?
So I don't think IO private smart contract requires any protocol level change because basically we can so IO can verify ideal IO implementation should be able to verify any ZK proof so that as long as we can make ZK proof compatible with today's Ethereum protocol, this should be also verifiable within IO. And for in terms of the improvement, yeah, this is a very interesting point. Yeah, one idea.
I think there's some
Yeah,
related questions here in the chat as well.
yeah,
Marius mentions, judging from the benchmarks you showed, it seems you're several orders of magnitude away from IO being applicable for real applications. I guess GPU acceleration will shave off an order of magnitude. What are your concrete steps to get to this, to get closer to this applicability? And Vitalik adds to that, on top of that, the multi-gigabyte size of obfuscated programs makes this quite far from viable for on-chain use. He'd be curious to understand how far we are from being able to massively decrease that. I mean, maybe you have some
yes,
thoughts on that, sorry.
yes. So, first of all, we don't necessarily need to directly put the obfuscated circuit itself on chain because the point is, as long as as long as the obfuscated circuit is available for anyone, anyone can download this and execute the private smart contract. So yeah, maybe like we need the data availability or verification when new private smart contract is deployed. But one way is if we have like instead of building the obfuscated circuit for each private smart contract, if we can make a generic or obfuscated circuit for any private smart contracts, we can So for example, community can make the trusted setup ceremony in similar to community did for Kezoji commitment ceremony. And as long as we can ensure that many people can already access to this obfuscated circuit, we don't necessarily need to store obfuscated circuit itself on blockchain, or we don't necessarily need to verify its data availability, because this is a one-time things. And in terms of the improving efficiency, we believe our GPU can increase the complete execution time around 10 times or maybe more. But we still need the theoretical improvement, because the size of the obfuscated circuit or its required amount of computation increase by the at least n power 3 order, where n is the input bit size. So we are researching a new theoretical construction, improvement of the theoretical construction, which can reduce this increase of the data size by reducing the lattice errors in similar to the FH's bootstrapping.
Got it. We have another question here. The examples for mixing and private matching have a state that grows linearly with the users. Is the cost of I/O evaluated super linear with the input? Is this a limit for performance of these applications? Could these applications do I/O evaluation with complexity below linear with the number of users?
Yeah, I think this is the one topic that we can explore, and we have not have the complete answer, but I think we might still have some bottlenecks for data availability check of the encrypted state data. I think we don't necessarily need to input all encrypted data into the IO. So rather than that, if we consider some kind of like Boolean based RAM based model, we can combine the protocol to. So for example, we might be able to combine some PIR protocol, which allow our client to fetch only the associated or some associated data from big database without revealing its query. So for example, IO program can behave as a trusted client of this PIR protocol, so that while IO program does not need to reveal its complete query, this can request untrusted party outside the IO evaluation to obtain some encrypted state corresponding to the queried index. And IO can verify that this is the correct result, at least by using ZKP.
Okay. We have another question here. I don't know if it's somewhat asked or answered already, but how do the benchmark results fit into the current Ethereum gas price model? You cannot run calculations for 100 minutes in a smart contract.
So first of all, I don't think we run the obfuscated circuit. We don't run the evaluation step of the IO on smart contract on layer 1. Rather than that, it's more close to the how ZK rollup works. Because if we only have one permissionless untrusted party who runs the obfuscated circuit off-chain, for example, if the obfuscated circuit can make the signature only on the output of the collect IO output, we can smart contract layer 1 can receive the IO output from IO along with signature. And if this output has a correct signature, we can immediately accept this result as the correct result. And this is secure if the signing key for this like output signature is hard coded only inside the obfuscated circuit. So in other words, if we like see this IO as a black box, you can think the public key or verification key or for which the signing key is held by this black box, trusted black box. And just this trusted black box makes signature only for the correct output of this black box. So in this case, you just need to layer one smart contract just need to verify the signature to check if this is a correct execution result of the obfuscated circuit or not.
Okay. We're getting close to the end of the call, but I'll take maybe one or two questions more.
Yes.
One here is how much more costly to the end user is a transaction with IO versus without?
I think this also like a this is also very similar cost model as ZK rollup. So first of all, end user does not necessarily need to directly evaluate this obfuscated circuit because for example, if the output from the obfuscated circuit is also again encrypted and your personal public key, even if anyone can get the output of your output of the obfuscated circuit for your some private input, or only you can decrypt this ciphertext. So this means in similar to our ZK lab, you can delegate the evaluation of this IO evaluation to untrusted party. So this cost depends on this depends on the market such that the party one untrusted party who has the best hardware with cheaper like a price can if there is one like a untrusted party who has a good hardware with cheap price our price transaction cost using this IO will decrease. So it's a almost similar cost model as the ZK rollup, ZK previous.
Okay. Um, okay. Yeah, Enrico, I see just made a comment here just to add on to that. I think that's it for all of the questions.